Good afternoon, grade 12s. Welcome to our telematics program for this afternoon. My name is Cyril Goldstone, and I teach at Blobergrund High School, and I'm very happy to be here with you for this Matric revision program of Term 1 subject matter. You know, there's a lot of work that you've done in Term 1. It's been an interesting term, and what we're going to do during this entire program is go through certain features of Term 1 work by looking at past exam papers as well as refreshing your memory in connection with some very important concepts that will prepare you for the final examination. So to begin, you'll notice from the monitor that the basis for our program is found in the learning material resource that your school has obviously issued to you, and there are many questions that can help you in that connection. First and foremost, we're going to have a look at paper 1, in particular question number 1. Now, you know from having a look at past Matric maths papers, question 1 generally is about 25 marks, 26 marks, plus or minus. And in question 1, the following points come up for examination. It's a revision of grade 11 subject matter involving the solving of quadratic equations and inequalities. Also, the use of the quadratic formula, which is found on the information sheet that you are given. Remember, that formula is x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. That is also examined. Then we have exponents and surds that are examined in paper 1 as well as simultaneous equations. You could either have a question that says, solve the following two equations simultaneously, or there could be a mathematical situation involving simultaneous equations. And then, of course, determining the nature of roots. In a very real sense, what we can say is everything in question 1, generally speaking, is drawn from grade 11 work. Now, you know that the Matric exam, the final exam in Matric, encompasses all our knowledge from grade 10, grade 11, and into grade 12. And therefore, it's so important to have a good start in Maths Paper 1. So we encourage you to really work on different questions from different papers, different schools, different provinces for that matter, in connection with question 1. Moving forward, today we're going to focus on number patterns. Now, this is a question that is generally question number 2 in Maths Paper 1. And in number patterns, questions will revolve around sequences and series, as you can see on the monitor. There we have sequences, either arithmetic sequences, geometric sequences, and quadratic sequences. Remember, the quadratic sequence was something that was done in grade 11. In grade 10, the arithmetic sequence, even in grade 10, the geometric sequence to some extent, right? So these three sequences come up for examination. And then when we add numbers together, you may recall we now get a series, not a sequence or a progression, but a series. In other words, 1 plus 3 plus 5 plus 7 and so on. And for examination now, in question 2, we have an arithmetic series, and then we have geometric series coming up, as well as convergence series. We're going to talk about that in a moment, as well as the sum to infinity. There's a nice formula in that connection as well. Now, grade 12s, do not forget that the examination guidelines say that you should be able to, in an exam, show the derivation of the formulae for the sum of an arithmetic series as well as the sum of a geometric series. These questions are generally 4 or 5 marks, and they are important. That's why we want to encourage you. We stress, make sure you know how to derive those formulae. You never know, the examiner could ask you to derive one of them, and how good it will be if you know exactly how to do that. Marks for free. Then also, in connection with number patterns, very important is this concept of sigma notation. Many learners battle with sigma notation. Some don't like sigma notation. Some feel it's very complicated, but it's a very important mathematical concept, and so we have to ensure that we master that. So in sequences and series, we now want to have a look at the various formulae that play off. Notice these formulae that are found on the information sheet. Let's have a look at them individually. In grade 10, we met this general formula here of the arithmetic sequence. The formula is Tn is equal to A plus n minus 1d. And the sum of an arithmetic series, which we met in grade 12, right, is given by Sn is equal to n over 2, square brackets, 2a plus n minus 1d. Did you notice that the arithmetic sequence as well as the arithmetic series are characterized by a common difference with the d? What about the geometric sequence? Well, here's the formula for the general term of a geometric sequence. Tn is equal to AR n minus 1. So there we have an exponent. Notice the R standing for ratio. And the sum of a geometric series is given by Sn is equal to fraction A, open brackets, R to the power n minus 1, close round brackets, divided by R minus 1, where R is not equal to 1. And we know R should never equal 1 because that will give an undefined sum in connection with that geometric sequence, series. So those are the formulae that are on the formula sheet. Now, in connection with the geometric series, there are two more that we want to highlight. Firstly, here we have this formula here, where we have this very interesting Greek alphabetic letter, and that is sigma. This is the sum to infinity. Sorry, that's the sum to infinity. There we have our infinity, not sigma, infinity. The sum to infinity is equal to A over 1 minus R. Once again, R should not be equal to 1. And for the series to converge, very importantly, the condition that is given for a convergent geometric series is that the ratio must lie between minus 1 and positive 1 as well. So on the information sheet, all these formulae are shown, and these are the formulae that you need to use, that you can use in solving questions in connection with number patterns. So let's have a look at our resource material. Do you notice there, on page 6 of our resource material, question 2 is drawn from the DBE paper, that's the Department of Basic Education, and that was the 2016 exam. And question 2.1 said, given the arithmetic series, and they give us a series A plus 13 plus B plus 27 plus ... Right? And of course, it's an infinite series because it's, there's no last term there, of course. Now, question 2.1.1 says, show that. Now, here's an important point. Grade 12s. When an examiner says, show that, what the examiner means is prove that that is the case. In other words, that is the answer that you should arrive at. Now, you can't say, yeah, it definitely is that, and therefore, No. You must work to that answer. That's point number 1. So you can't use that as the proof. You must work to that proof. Secondly, whatever happens after that particular part of the question means that you must use those values. And that's how you get your marks. Because perhaps you can't solve 2.1.1, but now you can solve 2.1.2 by substituting 6 for A and 20 for B, and there you have your series, and now things can make more sense to you, and you can take it from there. So let's have a look at 2.1.1. How do we show that A is equal to 6 and B is equal to 2? Notice that is 2 marks. So generally speaking, there's not a lot of calculation that is going to be done here, but there are certain things that we need to remember. Firstly, what we need to do is we need to recognize our terms. There we have A, 13, B, and 27. Now we know for an arithmetic sequence and an arithmetic series, term 2 minus term 1 must equal term 3 minus term 2. In turn, term 4 minus term 3 must equal term 3 minus term 2. And that is the basis for us starting our calculation here. Do you notice on the monitor? There we see term 4 minus term 3 must be equal to term 3 minus term 2. Well, what is term 4? There we have it here. It's the 27. Because if we look, the A is the 1, term 1. The 13 is the second one. B is the third one. And then 27 is the fourth one. So in a real sense, we're going to say now, if we populate that formula, 27 minus B is equal to B minus 13. When we do that, well, we solve it nicely, and the answer that we get for B is equal to 20. That's what we had to show. That's what we had to prove, and we proved it. Well, what about A? We do exactly the same. Term 3 minus term 2 should be equal to term 2 minus term 1. And then when we populate that formula, well, then we come up with A is equal to 6. Now we know, once we get to that point, we have our 2 marks in the bag, and we are going to victory. What is our next question? The next question in red, as you can see, says, calculate the sum of the first 20 terms of the series. Now, this word sum actually gives the game away. We must use the sum formula, and there we see the sum formula. There's the sum formula given us on the formula sheet. Sn is equal to n over 2, 2a plus n minus 1d. So if we populate that, now our formula, notice what we've done. We've inserted for A, the number 6, and we've inserted for B, the number 20. So we have this series that reads 6 plus 13 plus 20 plus 27 plus ... Now we've got numbers. We're no more working with A and B. Remember what I said? What you solve there in the first part needs to be carried on as a foundation, and you need to keep building based on what you've solved already. Now, when we find the sum, very important it is, as you can see on the monitor here, always itemize. Get a list of what you have already and what you are looking for. The question says, calculate the sum of the first 20 terms. Grade 12s, we know that n is going to be 20. We know that A is 6. We solved that in the first part. We know that D is 7 because 13 minus 6 is equal to 7. 20 minus 13 is equal to 7. 27 minus 20 is equal to 7. So there's a constant difference of 7 there. We are looking for S20. So when we populate our formula shown in green, there we have all the numbers put into place. And if you do that on your calculator, you'll notice that the answer for the sum of 20 terms is none other than 1,450. Now, at this juncture, may I also stress the following. Grade 12s, please get into the habit of answering the question. Sometimes what happens is learners see a question and they start calculating things, but the question is not asking for what they are calculating. You will not get marks for that. Make sure that you answer the question. And after you've performed your calculation, go back and see, now what did the question say? What did the question ask me to calculate, to determine? Have I done that? That is a very, very important part of mastering mathematics. In fact, it's an important part of life to know exactly satisfying answers in connection with questions that we have. Moving on to 2.1.3. The question says, write the series in question 2.1.2 in sigma notation. Now, if you have a look here, that series was 6 plus 13 plus 20 plus 27 plus ... Right? If we are going to write any series in sigma notation, what we have to find is the general formula that characterizes this particular series. Now we know A is 6. We know our constant, we know A is equal to 6. Our constant difference is equal to 7. And so we need to find our Tn. We don't know what that is, right? The defining equation, one can say, of that particular series. So let's explore that. Right, here we go. We have the following. Tn is equal to A plus n minus 1d. But you may be saying, but hang on, I don't know n. But that's the whole point. We don't need to know it at this stage. It must be part of our working out. So if we continue with this now, right, our Tn is going to be, our A, as we can see, is 6 plus n minus 1. Our D is going to be 7. And there we have the following. That's going to be 6. We multiply that in. That's going to be 7n minus 7. And here we have our Tn. That's going to be 7n. 6 minus 7 is minus 1. Right? Now, let's have a look and see whether this is what our equation really works out to be. And there we see on the monitor, there we have our general term. So how do we write this now in sigma notation? Well, there's the answer given to us. Now, let's have a look at this, because sigma notation can also be quite a complicated situation for many, many learners, but it needn't be. There's no doubt about that. So, in connection with our situation here, there's our sigma notation. This is the correct answer. Notice there's our 7n minus 1. So, the general term of our sequence, right, there's this answer here, 7n minus 1, needs to be put on the side of sigma. What about this number on top? What about this n is equal to 1? Well, you may recall that the number on top stands for the number of terms in the series. You remember in 2.1.2, the question explored the first 20 terms. So the number on top is going to be 20. And at the bottom, we start from the first term. Notice we don't write a 6 there. It's from the first term because the number of terms. That's why n means the first term. So the way to get that, as you know, is you say the top of sigma minus the bottom plus 1, right? And that's how we get the number of terms, and that's 20 in that case. In other words, 20 minus 1 plus 1. And there we have 20 terms. So here we have our answer in connection with sigma notation. We encourage you, grade 12s, to keep going through many examples in connection with writing situations in sigma notation. It is very, very important. Moving on now, question 2.2 says, given the geometric series. Now we know the geometric series. We've spoken about that already. A geometric series, like a geometric sequence, is unlike an arithmetic sequence. The arithmetic sequence has a constant difference. That's why there's a D in that formula. The geometric sequence, as well as the geometric series, has a ratio. So there's an R. And so you'll notice how this will play off in our different calculations. Now we are given a situation, x minus 2 plus x squared minus 4 plus, and now we have a cubic expression, x cubed plus 2x squared minus 4x minus 3, cubic polynomial, right? Plus dot, dot, dot. So we're given that geometric series. And now we are asked for 4 marks. Determine the values of x for which the series converges. Very important point. Grade 12s, there's only one condition for a series to converge, for a geometric series to converge. And we can sketch it this way. For a series to converge, here is the situation. Very, very important. Your ratio must lie between -1 and +1. That is very, very important. In fact, this is part of how we are going to find our answer. And of course, as you can see from this, once again, this includes inequalities. And so all our knowledge of inequalities will play off in connection with this. Well, let's go further, right? So there we have our term 1, as we can see it here. There's our term 1, x minus 2. Our term 2 is x squared minus 4. And there we have our term 3 here. So how do we find the ratio, right? The common ratio of a geometric series or geometric sequence? This is how we find it. Term 2 divided by term 1 must equal term 3 divided by term 2. In turn, term 4 divided by term 3 must equal term 3 divided by term 2. That's how we find the ratio of any geometric series or any geometric sequence as well. So what does this mean in terms of our calculation now? Well, we use exactly that. And we recognize that that is how the series will converge if the ratio lies between -1 and +1 as well. So the ratio is found by taking term 2 divided by term 1. When we substitute those values in, notice we factorize here. And then as we factorize, there we'll notice that our ratio now is x plus 2. That's what we come up with. So we take this x plus 2 and we're going to put it in this formula that I've written here, right? We're going to put it in here. X plus 2 is going to go in there. So notice now what happens. Here we have -1 is less than x plus 2 less than 1. And you may remember in grade 10, you had an inequality that looked like this. And the way to solve this inequality is to start in the middle. You see, we only want x there. So what we need to do to the middle is to subtract -2. In other words, we say -2 here. And because we've done it in the middle, we must say -2 on this side here. And on this side, we must also say -2. So in a very real sense, if we have to write that out, it will look something like this. -2, -2, -2. And now, if we have to simplify that, we know that 2 minus 2 is going to be 0, so we're going to be left with an x here. That's what we want. And -2 minus 1 is going to be -3 there. And this side, 1 minus 2, we know that this is going to be -1. Here is the solution to this particular mathematical situation. There is our answer right here. Very, very important. Now let's see how this plays off in connection with what we find on the monitors there. When we put that in there, right, you'll notice that that's the case. And there we have that. And there's our solution given us there, which is what we found right here in green as well. Right? So that's how number patterns play off there in connection with geometric sequences and series. Look at this question now. 2.2.2. If x is equal to -3/2, calculate the sum to infinity in connection with the given series. Well, the sum to infinity, as we established, is equal to a over 1 minus r. And so if we populate that, what we've done now, notice here, we've highlighted the x in pink. Can you see that? Right? It won't be done like that on your exam paper. But just to show you where we must put the value -3/2, we've put it in here. A, as you know, is x minus 2. 1 minus r, there's our ratio as well. And there we have it. So when we substitute that in there, in terms of numbers, we're going to have something that looks like that. And then if we simplify that, the sum to infinity is equal to 7. Very important principle. We must know how to work with sum to infinity in connection with geometric series as well. Now let's move to question number 3 in our material that you have been provided as Term 1 Mathematics Revision. Here is the question, and the question is drawn from a past Matric exam paper that explores the quadratic number pattern. And the question says, if you notice the monitor, the first 4 terms of a quadratic number pattern are -1, semicolon, 2, semicolon, 9, semicolon, 20. The question, determine the general term of the quadratic number pattern. And they give us 4 marks for this. Now, you may remember that in grade 11, you did a lot of calculations in this connection. What we need to do now is to find this general number pattern of the quadratic sequence. And first and foremost, what we need to do is we need to write our numbers here. -1, and there we've got a 2, there we've got a 9, and there we've got a 20. Right, so that's step number 1. Now we know that for the quadratic number pattern, we have an arrangement that should look something like this, and I'll explain it in a moment. Our second term in the opening line minus our first term should give us this term at the bottom here. So in other words, when I say 2 minus -1, I'm actually saying 2 plus 1. Do you notice that? And that number is, as you know, 3. Then I say 9 minus 2, I'm going to get a 7. And then 20 minus 9, I'm going to get an 11 there. Do you notice what we have? 3, 7, 11. Grade 12s, here's an important point in connection with quadratic number patterns. This is the row of first differences. 3, semicolon, 7, semicolon, 11, semicolon. The row of first differences of every quadratic number pattern represents an arithmetic sequence. Please do not forget that. Every quadratic pattern's first row of differences represents an arithmetic number pattern, an arithmetic sequence. And the peculiar thing about a quadratic number pattern is that it has a second constant difference. You know that from grade 11. But you know, sometimes we forget what we did in grade 11. We're so happy that we passed. Now we're in grade 12. This comes up for examination in grade 12. So what are we saying? Well, we're saying the following. Now, once again, we must find out a little bit more. So if we take now our 7 minus 3, we know the answer. We're going to get a 4. And 11 minus 7 is going to be 4. Here we have our row of second differences, constant second difference. There's our row of first differences, which is an arithmetic sequence. And there's our opening line for the quadratic sequence. So now we know that the formula for any quadratic number pattern, which occurs on the information sheet in your matric exam paper, is given by the formula Tn is equal to an squared plus bn plus c. So how do we find the values of a, b, and c? Very easy. You remember from grade 11, we say 2a must equal whatever this number is here. Then we come here and we say 3a plus b must equal to that. Whatever we get for a here, we substitute for a here, and then we work out b there. And then here we say a plus b plus c, that should equal -1. Now with this in mind, let's keep going further. If we have to find out the value of a, remember we had 2a is equal to 4. Well, it's very easy now. We can solve for a. Therefore, a is equal to, you divide both sides by 2, a is simply equal to 2. Here we've got our value of a. What about b? Remember, we already established that 3a plus b should be equal to 3. So we take this, but now we're going to substitute the value of a, which is 2, into this here. So we're going to have a situation where we have 3, 2, plus b, and that's equal to 3, right? And so we know that 2 times 3 is 6. We take that 6 over, it becomes -6. So therefore our b is equal to -6 plus 3, -3. How do we find the value of c? Once again, we say a plus b plus c is equal to -1. We've got the value of a. Have you got your calculator there? You're working with it? The value of a is +2. We know the value of b. The value of b, as you can see, is -3. So now on your calculator, 2 minus 3, or 2 plus -3, which is -1. Take that -1 over, and that -1 changes to +1, +1, -1. The value of c is 0 in this particular instance. So let's just write this down. C is equal to 0. So what is the general term of our quadratic sequence? Tn is equal to an squared plus bn plus c. We know that a is 2, so therefore Tn is equal to 2n squared. B is equal to minus 3n, and C is 0, so we can just leave that out. Here, grade 12s is our final answer. That's how we find the general term of the quadratic number pattern that we are dealing with. Do you notice that? Very, very important. Now, as I mentioned, this is all part of the grade 11 syllabus, but it's so important. It comes up for examination, and it came up for examination in a past grade 12 paper, so it's very important, and they are very easy marks to actually achieve. The more exercises you do, the more question papers you work through, the more skill you get, which is so important in mathematics. Remember, plan your work, then work your plan. Very, very important. If you take that philosophy to different parts of mathematics, even physical sciences, all your subjects for that matter, you'll go very, very far. If you plan your work, then work your plan. Now, we're moving on with this particular question. This question went on to say, calculate the value of the 48th term of the quadratic pattern. You may remember we've just established now by means of calculation that the general term looks like this. Tn is equal to 2n squared minus 3n. So they're calling for the 48th term. That means n is equal to 48. So we simply substitute 48 there, and there we have it. It's none other than 4,464. That is the quadratic number pattern. Then question 3.3, show that the sum of the first differences of this quadratic pattern can be given by Sn is equal to 2n squared plus n. That's 3 marks. Now, arguably, there could be more ways than one in which this could be done. But now notice here how we approach this. Here we have on the monitor, there we have our different terms, right? We saw that at the start. There's our row of first differences in blue, 3, 7, and 11. And so there we have the sum of the first differences. That is an arithmetic series as it is right there. So we've got our A, we've got our D, right? We don't know n because it needs to be part of the solution, so we can fire away. And this is what we do. As we take it further, there's our formula, which we get from the information sheet. And when we substitute into that formula, there we have all our numbers going in there, and then we come to our solution. Finally, there's our solution. Sn is equal to 2n squared plus n. Very important. So, when answering questions on number patterns, remember, plan your work, then work your plan. Always ask yourself, what do I need to determine? And how can I best determine it? If you keep that in mind, grade 12s, as you see on the monitor, these important points, you will go to success. Plan your work, then work your plan. And ask yourself the questions, what do I need to determine? And how can I best determine it? Now, something else that we need to talk about is this matter of functions and graphs. Now, we know from grade 11, there were many functions that we dealt with. The straight line, we dealt with the parabola, we dealt with the exponential graphs, we dealt with the hyperbola, right? All these functions are very, very important. Of course, in grade 12, it goes further than that. We don't just deal with those functions. Now we look at inverse functions as well, right? And in our term 2 program, when we revise that with you, you'll see how we'll help you with the revision in connection with inverse graphs. Let's have a look at the equation of a straight line. We know that that equation is y is equal to mx plus c. And then, of course, the m stands for the gradient, which is given by the formula y2 minus y1 over x2 minus x1. And the c in that formula stands for the y-intercept. If the gradient is positive, the line will go in that direction. In fact, the line has the gradient similar to the line y is equal to positive x. If the gradient is negative, well, the gradient will go in that direction there. And so there we have it. Now, what about the quadratic function, the parabola? The parabola is given by the equation y is equal to ax squared plus bx plus c. If a is greater than 0 or positive, we're going to have a minimum value parabola. Remember the emoticon? He's smiling. He's got minimum problems there. What about if a is less than 0? Oh dear. Well, he is negative. He's got maximum problems. He is not smiling. He's got a negative outlook. And so there we have our parabola being sketched. There we see the y-intercept shown. There we see the axis of symmetry, which is given by the equation x is equal to minus b over 2a. And if we go further, the coordinates of the turning point, now we have that formula. It can also be written like that. There we have the turning point. Look at that example. Y is equal to x minus 2 all squared minus 4. If we have to find the coordinates of the turning point of that particular parabola, notice x minus 2 all squared minus 4. Grade 12s, it's very easy. If we take what's in this bracket here and force this to equal 0, x minus 2 is equal to 0, therefore x is equal to positive 2. So the coordinates of our turning point can be written as positive 2, there's our x value, and then we go for what is here, including the sign. We bring that right down here, and that's minus 4. And that's what we will see on the monitor here. The coordinates of the turning point in connection with that parabola are 2 and negative 4. Don't forget how we find the coordinates of our turning point. The x-intercepts are found by making y equals 0, and there are also inequalities that play off. Remember, above the graph means positive, below the graph means negative as well, and there it all plays off. Now, in the source material, there's a very interesting question. Question 6. We just want to walk you through this one, right? Because this is grade 11 work, and it's very, very interesting, and it's important that we understand what is really taking place. Notice that question begins by saying, the sketch below shows the graphs of g of x is equal to minus 12x plus 12. So that's obviously a linear function or a straight line. And f of x is minus 3x squared minus 9x plus 30. Notice grade 12s, just as a little detail, in all the telematics material, the reference is given there. Now there's a reason for that. The reason for that is we want you to develop a self-directed study approach. Remember, from grade 12, you're going into a tertiary institution, perhaps a university or a college. The lecturer is not going to give you homework. The lecturer is not going to be like a school teacher who worries, why are you not working in class? You must develop the maturity to work on your own. And so we encourage you to please take the ball and run. In other words, work through as many past exam papers as you can. And where you have problems, ask your teacher. Ask learners in the class who are very good in mathematics. If you have a tutor, you're working with a tutor, ask your tutor as well. But the more exercises you do, the more skillful you'll become, and your self-confidence will be boosted. Getting back to this question, we read that A and B are x-intercepts of f. So there's A and B. We now have to find them, don't we? Because we let y equal 0, and then we solve that using the quadratic equation means of f, and C is a point on f. There's C right there. D is a point on G such that CD is parallel, notice, parallel to the y-axis. That's an important point because you know from analytical geometry that parallel lines have equal gradients, not so. And so the gradient of the y-axis, what is the gradient of the y-axis? It's 0. There's no gradient, right? There's no slope. In fact, the equation of the y-axis, as you know, this equation here is where x is equal to 0. That's the equation of the x-axis. So therefore, this line here will have no gradient. Whatever the x value here will be, that will be it. For example, if this value here is -1, the equation here will be x is equal to -1. If this value is -3, it will be x is equal to -3, and so on and so forth. Keep that in mind. Very important. And then they further tell us that h and k are points of intersection. Now, that's a very important detail, because the way we find points of intersection is we simply take one part of that formula and we force it to equal the other part, solve for x. When we find our x values, we can substitute them into any one of the equations and find the corresponding y values. But let's look at the questions that they give us. Firstly, they tell us, or they ask us here, question 6.1, here, determine the length of AB. They're looking for this length, AB, right? So very, very interestingly, if we've got these x-intercepts, well, then we can find that length. Find the coordinates of k. There are the coordinates of k. Notice that's a point of intersection between the straight line and the parabola, so that can easily be found. Then we come to a question involving inequalities, greater than, less than, and so on. Very easy. And the maximum length. We encourage you to work through this question as well. Now we come to the hyperbola, also another function. And of course, the hyperbola is given by this equation here. And of course, we know that there we have our x asymptote and y asymptote as well. Remember, the asymptotes are points where the graph is undefined. In other words, we can say the asymptote lies on a particular line in that case, and you'll notice a sketch by means of a dotted line, right? When we take it further, when a is less than 0, we have diagrams that look like that. Notice when it's negative, it's going to look like this, and the hyperbola, when a is positive, will be in the first and the third quadrants. For negative, the second and the fourth quadrants here. Moving forward, here we, pardon me, here we have a question that you can explore. This is question number 4 in our source material. It's a very interesting question on the hyperbola. We encourage you to have a look at this because there are many important points that you can work through, many important points that can really strengthen your knowledge in mathematics. Moving on to the next function is the exponential graph. And the exponential graph, as you know, has the standard form y is equal to a b to the power x plus q, where that q, the y is equal to q, right? And as you can see there. And so these situations are mentioned here in the telematics material. Please have a look at them. They are about the shape of the exponential graph. Very important. There was a question in connection with the exponential graph that occurred in one of the exam papers. Notice this question here. It says, sketched below is the graph of h of x is equal to a to the power x for a is greater than 0. R is the y-intercept of h, the points 2 and 9, and b and 1 over 81 lie on h. And then the questions explored. Write down the equation of the asymptote of h. Grade 12s, this is very easy. Here's the asymptote of h, right here. Do you notice that? It's the so-called x-axis. And the equation here of the x-axis is y is equal to 0. That's the answer here. Then 4.2, determine the coordinates of r. Look at r. We know that the exponential graph always passes through this point. The coordinates of this point, none other than 0, semicolon, positive 1. That's the exponential graph. And then if we calculate the value of a, we can choose any point on the graph. Suppose I choose this point, 2 and 9. That's very, very easy, right? Remember, if we go back, the equation said h of x is equal to a to the power x. In other words, y is equal to a to the power x. And now, if we look at our diagram and we substitute the point P, which has coordinates 2 and 9, very easy. What do we come up with? Well, where the y is, I'm going to put a 9. I've still got my a, I'm finding that. And where the x is, I'm going to put a 2. So I have a squared is equal to 9. How do I find a? Well, a is going to be 3, right? If I find the square root. And I know it can never be negative because here in this particular situation, I'm told that the A is greater than 0, so we're only looking for the positive. So A is equal to positive 3. So what have we been saying in our program this afternoon? If we had to take the sum of what we've discussed, remember Maths Paper 1, very important. Written on a Friday, it contains question number 1, which has a whole lot of grade 11 principles that are examined. Things such as the quadratic formula, things such as inequalities, simultaneous equation, the nature of roots, very important. It's about 25 marks. Make sure you score lots of marks in that connection. Then, the next question, question 2. Now we start number patterns. We had a look at the arithmetic number patterns. We had a look at the geometric as well as the quadratic. And we even had a look at arithmetic series, geometric series, and all sum to infinity as well as sigma notation. Then we went on to our functions, the straight line, the parabola, the hyperbola, as well as the exponential graph. Grade 12s, practice, practice, practice. That's what will get you your marks in the exam. You'll become more skillful. It will boost your confidence. Don't give up and don't give in. And in everything you do, plan your work, then work your plan. Keep working hard on your mathematics. We know you're going to succeed. And all the best with your onward academic journey. Bye-bye.